Vint Cerf, father of the Internet.
Vehicles pitching downrange.
We are at I would say, a very important inflection point, because between SpaceX and Blue Origins, for example, among others, we're starting to see serious efforts to return to manned space travel and potentially come back to the moon on more or less quasi-permanent facilities, laboratory facilities, habitats, and then eventually, perhaps in the 2030s, a mission to Mars. So the group that started with a small, half a dozen people has now grown well beyond that to include most of the NASA laboratories and the European Space Agency, the Japanese Space Agency, the Korean Space Agency, and the Consultative Committee on Space Data Systems. We began prototyping this software in 1998. We were forced to put up a store and forward system in 2004 when the two rovers, Spirit and Opportunity, landed on Mars with the intent of transmitting data directly from the surface of Mars back to the Deep Space Network at the blazing speed of 25 kilobits a second. Of course, the scientists were moderately grumpy about that. And then when the radios were fired up, my understanding is that there was a problem with overheating. And of course, the engineers said we had to back off on the duty cycle, which meant there would be even less data coming back. Now the scientists are particularly grumpy. But it was noticed that there was an X-band radio on the rover, and rovers, plural, and X-band radios on the two orbiting systems, which had been sent to map the surface of Mars before the rovers got there to figure out where the rovers should go. So both the orbiters and the rovers were reprogrammed to do store and forward packet switching to deliver the data back to Earth. And here's the cool part. Because the orbiters were not very far away from the surface of Mars, the X-band radio delivered 128 kilobits a second. Because the orbiters were out of the atmosphere and actually had more power from the solar arrays that they had available, they could transmit back to the Deep Space Net at 128 kilobits a second. So for all the time since 2004, the rovers and their subsequent space landers and rovers have been transmitting data through this relay system. So virtually 99% of all the data has come back from Mars through a basically packet switch design. In the meantime, since that 2004 period, a group of engineers, both at NASA and also with some of the other space agencies, have been refining the interplanetary internet design with a suite of protocols we call the bundle protocol suite. It includes something kind of like the internet protocol layer, which we call bundle protocol. And in addition to that, we have some lower layer link level stuff like the Licklider transport protocol and applications to go on top of the bundle protocol. All of those are becoming fully standardized. So the Consultative Committee on Space Data Systems, which is a UN related agency, has standardized the protocols, and so has the Internet Engineering Task Force. So we have terrestrial standards available. We have a number of implementations of the bundle protocol available on different platforms. And one of the more interesting DTN style experiments that's been going on for probably 6 years or so is in the northern part of Sweden, where the Sami reindeer herders are. They've hung little battery-based radio transceivers to track the reindeer as they move around. And of course, because their connectivity is erratic, the delay and disruption tolerant capability of the bundle protocols is important. Now, to be precise, they are not using the standardized bundle protocols because they needed to keep things really small and not consuming too much power because it's a battery-based system. So they have a kind of LoRaWAN style, low data rate signaling system. When they get to a central location after storing and forwarding through various relays, Then they switch on the full bundle protocols and they could go all the way to Mars if you wanted to. We're also just beginning to bring up those protocols, the bundle protocol suite, on all three of the cloud-based systems at Amazon, at Google, and at Azure. And the idea there is to have servers that are running the bundle protocol suite, and then a whole bunch of applications running in laptops or mobiles or pads or something in order to exercise the bundle protocol at scale and to test the network management system. But in the bundle protocol world of interplanetary space, where the distances are literally astronomical, you don't know when you're going to get a response back. It could be 40 minutes round trip time to Mars and back when we're farthest apart in our orbits. It just gets worse when you get out to Jupiter and Saturn and the outer planets. So you have to rethink the way in which network management functions when you have extremely high latencies involved and uncertainty about when data will be delivered. So we want to test as much as we can of those things terrestrially, because it'll be a lot easier to fix here than it will be when things are 250 million miles away.
No, I think it's absolutely amazing, and so I'm hopeful. It sounds like that we'll get past 128 kilobits per second in the next round, right? Is it? Because I think the big issue when I was reading some of your recent writing about the DTN protocol, the challenge is actually the limitations on the speed of light and the ability to actually to try and maybe that leads us to a different subject. Is this going to be a quantum computing type of solution that will solve this going forward? Or what's your thoughts on how do you get the speeds up to where we can be transmitted something immediately back from Mars?
Well, wait a minute now. Remember that high speed, high data rate does not do anything about the latency. The latency is a speed of light problem. And Mr. Einstein tells us that there's a speed limit in space. It's 300,000 kilometers per second. And so the rate at which we can transmit data is not related to the latency at all. It is related to distance, of course, because signal levels fall off as the square of the distance. So by the time you get to Mars, you have a very weak signal potentially. That's why we have to have big 70-meter dishes in order to detect a very weak signal coming back from the various rovers and orbiters. So the DTN is designed to deal exactly with this very, very long round trip times, which we can't do anything about. There is, however, some hope that we could get the data rates up, which would allow us to transmit more data per second. So there have been tests using lasers going to a vehicle in orbit around Mars. We were able to demonstrate a data rate on the order of about 600 megabits a second using a laser communicating to a vehicle in orbit around the moon. I'm sorry. Of course, if you go farther and farther away, the data rates aren't sustainable because the signal levels drop off, and you need more coding, for example, in order to deliver a successful signal and properly decode it. So by the time you get to Mars, we aren't going to be going 600 megabits a second, but it will certainly be better than 28 or 128, we hope. Keep in mind, though, that a laser signal is going to, the beam will spread even if it's a collimated laser. And so we will lose a certain amount of power because the antennas can't be infinitely big. So it will be a significant challenge, but there is a great deal of interest in doing laser-based communications for deep space missions. What I'm hoping, quite honestly, is that we'll use the moon and the return there to be a staging area for testing the robustness of the DTN protocols so that when we do go to Mars, we'll have confidence that those protocols will work in spite of the increased latency.